Now if you look at the important factors considered in combustion chamber design, so here two main combustion chamber design categories for diesel engines are shown. The first chamber is where you have the fuel injector here. This is the piston. The fuel is directly being injected in the combustion chamber. This is called direct injection combustion chamber. Fuel is directly injected in the main chamber. In the second chamber you can see this is the combustion chamber, and then here you have a swirl chamber. The fuel injector is injecting fuel in the swirl chamber. So this is called divided chamber, because here you see the combustion chamber is divided into two parts and you are injecting the fuel in one. This is called indirect injection engine or indirect injection combustion chamber design. Okay, so the important factors that need to be considered is what should be the heat loss to the combustion chamber wall. Suppose you have an injection chamber design which has large surface area. So if you have large surface area, then what will happen? Whatever heat is being generated inside the engine combustion chamber will be lost to the surrounding with large surface area, because large surface area is going to increase the heat transfer through the walls. So this should be as minimum as possible. Then what should be the injection pressure? Okay, this is also governed by the combustion chamber design. Nozzle design, what should be the nozzle design? How many numbers of the nozzles should be there? What should be the size of the nozzles? What should be arrangement of the holes? This is all governed by combustion chamber design. What should be the maintenance of the engine is also governed by the combustion chamber design. What should be ease of starting? There are some combustion chamber designs where it is fairly easy to start the engine. Well, there are some combustion chamber designs where it is difficult. For example, if you have a combustion chamber design where the surface area is quite large, when the surface area is very large, and if you want to start the engine in the winter time, as you start cranking, it has large surface area, so the heat loss in the beginning will be very high. Okay, as a result, the engine will not warm up. It will not warm up enough so that the fuel start evaporating, and therefore starting the engine in the cold weather will be difficult. So ease of starting is another factor. Then there are some applications where you don't want very expensive fuels, you really want very cheap fuels. For example, marine, I gave you an example of marine engines where it is required that you use very cheap fuels. Okay, so the ability to use less expensive fuels is also dependent on what is your combustion chamber design. Then utilization of the air. So basically you would like to utilize maximum amount of air possible in the combustion chamber. Then weight relation of the engine to the power output is also affected by the combustion chamber design. Then capacity of variable speed operation. For example, there are some engines which are operated always at fixed speed. For example, generator engines always operate at 1500 RPM, whereas the automotive engines operate from 600, 700 RPM all the way to 5000 RPM, right? For a car engine typically. So this is also affected by combustion chamber design. Then smoothness with which forces created by the expanding gases are transmitted to the piston. So this is also affected by the design of the combustion chamber. Now this slide is extremely important, and I would like to request you to give attention to this. What it shows is here in this first column, systems parameters are shown. This shows the 4 different designs of direct injection combustion chamber. This shows 2 designs of indirect injection combustion chamber. Okay, I already showed you what is direct injection, what is indirect injection. Now we will review this particular slide at the end of the lecture as well. There are 4 designs in the DI engines. First design is quiescent combustion chamber. Quiescent by name itself says it's quiet. Okay, quiet really means that there is hardly any air turbulence. Okay, so there is air is not playing really any role in mixing of the fuel and air. Okay, air turbulence is not playing any role. Then there is medium swirl. Medium swirl means there is air motion, there is swirling motion. By the way, what is the difference between swirl and turbulence? The swirl is the air motion in a particular direction, and turbulence is random air motion. It is not directional. Okay, so this is the main difference. So here in diesel engines we would like to have we have one design called medium swill, another design called high swill. High swill means the fuel air mixing is essentially largely a responsibility of air motion. Okay. Then there is high swirl, medium spray. So these are 4 designs. And in the indirect injections there are 2 designs, swirl chamber and pre-chamber. Okay. I will first discuss with you the direct injection combustion chamber. So as I mentioned, quiescent chamber, if the air turbulence is just not there, then how you are going to mix the fuel with the air? There are 2 things which are responsible for mixing of fuel with the air. One is the fuel droplets formation or fuel spray formation. The second is air mixing because of the air movement. So if the air motion is not there, that means it is expected that the responsibility of mixing fuel with the air is entirely the responsibility of fuel injection equipment. You have to inject the fuel at such a high pressure that the droplet size is very small, because now air mixing is not there, the air motion is not there. So the mixing with the air will entirely be the responsibility of fuel injection. So in this case, this is the largest size engine with very high fuel injection pressure, because the droplet size is supposed to be, fuel spray droplet size is supposed to be very small. Okay. When you say medium swirl are medium engines. Okay. And if you look at the size, largest engine will have a bore of 900 millimeter to 150 millimeter. 900 millimeter means about a meter. Okay. So the largest possible ship engines are quiescent type of combustion chamber. Okay. 100 is 6 inches, so almost this big. Okay. Medium swirl is more like truck engine. Okay. And here the size is 150 to 100 millimeter, which is 6 inches to 4 inches. Then you have high swirl. So high swirl, the size is even smaller, 130 to 80, about 5 inches to 3 inches, and the smallest one is 100 to 80. Okay. It is not possible to make engines which are smaller than 2.5, 3 inch bore. Okay. It's not possible to make diesel engines in sizes smaller than that. Okay. So if you look at the ship engines, there could be 2-stroke, there could be 4-stroke, medium swirl, high swirl and high swirl medium spray, all of them are 4-stroke engines. These could be turbocharged engines or supercharged engines, ship engines, and rest of them could also be turbocharged or naturally aspirated. These engines are never naturally aspirated. Most of the time they are either supercharged or turbocharged, but the remaining 3 can be both. It's possible to have both. Speeds, if you look at the largest bore size, so if the bore is large, obviously the stroke will also be large, and the stroke will be very large, the speed has to be slow. These engines are maybe 60-70 RPM to 2100 RPM. Larger is the bore size, smaller will be the RPM. In fact, ship engines, they could be 50-60 RPM. Largest possible ship engines operate at very, very slow speeds. Okay, but you can imagine even at 60, if the stroke is 3 meter, even at 60 RPM, it will be mammoth amount of mass that is moving up and down with piston and connecting rods. Okay, so in this case, if you look at this bore to stroke ratio, stroke to bore ratio is 3.5 to 1.2. That means if it is 1 meter piston dia, bore dia, the stroke will be stroke could be up to 3.5 meter. Okay. Here bore to stroke ratio is more normal, 1.3 to 1. This is 1.2 to 0.9. This is 1.1 to 0.9. So basically these 3 are relatively smaller engines, so their bore to stroke ratio is not very abnormal. In this case, the bore to stroke ratio could be very skewed. Okay. If you look at the compression ratio, the largest possible engines have smaller compression ratio. Why? Because these are very big engines, the amount of mass that is put in is huge, and if their compression ratio is very high, the pressure at the end of combustion will be so high that it will be very difficult to make a safe structure. Therefore, the compression ratio is reduced, and Generally ship engines have a compression ratio of 12, 13, like that. Even locomotive engines have the compression ratio in that range. This is bowl-in piston, this is deep bowl-in piston, and this is also deep bowl-in piston. So if you look at the shape of the combustion chamber piston, this is the quiescent chamber. Of course, I am talking about piston shape. This is quiescent chamber. If you look at bowl-in piston, this is bowl-in piston. Okay, deep bowl-in piston. This is deep bowl-in piston. This is also called M-type, man-type combustion chamber. Okay, this chamber was developed first time by a German company named MAN, which makes trucks, MAN trucks. Okay, this was invented about 100 years ago. So airflow pattern in this engine will be quiescent. In this case, it will be medium swirl. In this case, this will be high swirl, and highest swirl is in this smallest engine. Okay, nozzle holes in this case will be multi-hole. So one injector will have several holes, and you will be injecting several jets from the injector. In medium swirl also, you will have several holes. In high swirl, the injector will be only single hole. So if the injector is here, it is injecting in only one jet. Okay, in the medium swirl, in the high swirl medium, there are multi-hole injectors. Injection pressure, as you can see in the quiescent chamber, it has to be extremely high because mixing is only the responsibility of fuel injection. In this case, it is high. In this case, it is medium, and in this case also it is high. When I am saying high, low, how much high I am talking about? So this quiescent chamber could be easily 1000 bar, 1200 bar, 1600 bar, or even more. Higher the injection pressure, more cleaner your engine will be, because finer droplets will be produced and their combustion will be better, and they will be more environment friendly, they will be more efficient. Okay, so this could be very high. When you say medium swirl, this high means about 800 to 1000 bar, high swirl means about 600, 700 bar, and so on. If you look at the indirect injection systems are one of the smallest diesel engines possible. So you can see that here this is 95 millimeter to 70 millimeter diameter. So smallest possible engines could be made if they are IDI engines, not DI engines. Both of them are 4-stroke. They could be either naturally aspirated or turbocharged. The speed, if you look at the speed is increasing in the direction as the bore size is reducing, the speed is increasing. Highest possible speed is possible with IDI engines. IDI engines are actually faster in terms of RPM compared to DI engines normally. Okay, bore to stroke ratio is 1.1 to 0.9 in both of these cases. But if you look at here, IDI engines have some of the highest compression ratios also. Okay, so their compression ratio could be as high as 20 to 24. In DI engines, that kind of compression ratio is not possible. Okay, because of the emissions and efficiency requirements, now for DI engines, the compression ratio, I am talking about small DI engines for cars and things like that, it is getting stabilized at 16.5 now. Similarly, for spark ignition engine, the compression ratio is getting stabilized more at 9.5, 10. Okay. If you look at the airflow pattern, this is very high swirl in the pre-chamber. Here it is very turbulent. So you have to understand, this is swirl chamber. So that means the airflow is swirling. It has a pattern. This is pre-chamber, or also sometimes called turbulent chamber. So here it is turbulent. There is no particular pattern of the flow inside. That's why it is called pre-chamber or turbulent chamber. Nozzle holes, both of these have single hole nozzles, and the operating injection pressure is very low. How low? It could be like 400 bar, 200 to 400, 450 bar. So these type of engines have very low injection pressure. Why? Because it's okay if the droplets are large, we will mix it with air motion. Simple. So these are the pictures, as I mentioned to you, which explain these, show the cut section of indirect injection engine and a direct injection engine. This is the valve, this is the fuel injector, and you can see this is the bowl, piston bowl, and here you can see this is multi-hole injector injecting the jets directly inside the main chamber. There is only one chamber, main chamber. Here on the other hand, you have one chamber and there is another chamber. So this is indirect injection. Fuel is injected here in the single jet. You can see the fuel injector is here. This is what is called glow plug. Okay, glow plug is only required in IDA engines and not in DI engines. If you look here, for such a small volume you have very high surface area, right? So high surface area means when you would like to start the engine from cold, it will lose a lot of heat to the surroundings and the engine will be difficult to start. So to overcome, what you have is you have a finger heater. It's a ceramic based finger heater which is called glow plug. So before you start the engine, you allow the flow of electricity into it. So what happens is that this becomes red hot, and once it becomes red hot, what it will do? It will do radiative heat exchange with the walls of the pre-chamber and make them little warm. So when you do the compression, the heat lost is not, that much heat is not lost from the compressed air, and it does not cool down to very low temperatures, and you are able to, as a result, you are able to start the engine without much of a difficulty. And that is why every IDA engine is equipped with glow plug. You will not see this in DI engines. Here the single jet is coming out, but then you don't want this jet to go directly in the main chamber. So there is a stop here. Okay, so this is called fuel swirler. So basically it's like a block. You know, you have created an obstruction, the jet is coming and it is not allowing the fuel to go directly. It is stopping here and allowing it to remain inside the pre-chamber. So that's what is shown here. So the main difference between DI and IDA is clear. I will come to more details in my next slides. Is this clear? Now this is the main feature of the DI combustion chamber. As you can see, this is the injector. This is the omega shaped piston recess, okay, cavity. This is omega, okay, and this is glow plug. Well, some engines can have glow plugs. Normally it is not there in DI engines, but some of them can probably have. Nowadays most of the engines don't have any glow plug, DI engines. The main advantage of direct injection combustion chamber is that it is more economical. Its fuel average mileage is about 20% higher than IDA engines. Okay, for DI engines, omega piston recess is most widely used. So this design is used mostly in DI engines. So if you just look at any piston and you see omega recess, you can say that this engine is a direct injection engine. It has lower combustion surface wall area compared to combustion volume in comparison to IDI. So therefore the heat losses from this will be lower as well. More combustion taking place in and on the piston and less contact with the coolant. So when the fuel is injected, the combustion will take place here in this zone. Coolant is on this side. Okay, so coolant is not, I mean, you are having very little heat exchange with the coolant, and therefore the efficiency of the engine will be relatively higher in this case. Glow plug, again, you know, the same function. If cold starting, glow plug is only activated in the beginning of the starting of the engine, only for like first 10-20 seconds. After that it is cut off. It has no role to play. But DI engines, most of the modern DI engines really don't have glow plugs. It is mostly a requirement for IDA engines. Now I am going to discuss three main combustion chamber designs with you. First one is quiescent combustion chamber. The second one is bowl in piston chamber with swirl and multi-hole nozzle, and the third one is M-type combustion chamber. These are the three that I have made here. Okay. So if you look at the first design, which is the largest size of combustion chamber, also called quiescent chamber with multi-hole nozzle, typical to larger engines or large size engines. So you can see this is very shallow dish here. Very shallow. It's not very deep. okay, and this is basically the side view and this is the top view, okay. So this is the injector. Normally the injector is straight, okay, in quiescent chambers, and it is multi-hole. So you can see that from the injector there are many jets that will come out. It could be 6, it could be 8, it could be 12, depending on what is the bore diameter. Larger will be the bore diameter. You would like to use maximum amount of air, so therefore you will require to have more number of holes. Smaller will be the engine, lower will be the number of holes in the injector. So if it is like 1 meter, then you would like to have 12 jets coming out, because then you will have each jet will be able to utilize air only in a particular area. It can only be wide, say 20 or 30 degree, okay. Second is bowl in piston chamber with swivel and multi-hole nozzle. So you can see this is deep bowl in piston, also called omega shaped design. So this is the second design. You can see this is the section here, and in this design the injector is inclined. It is not straight. You can see in this it is straight, in this it is inclined, and also you will see that in this design sometimes this bowl is not really in the center, it is slightly off center, okay. And here this is multi-hole injector, so you can see this multiple holes, you have fuel coming in. So this is these are the jets of the spray, and because it is the bowl is located slightly off center, there will be some air swivel motion. So this air swivel motion will come out, and you see here the fuel injection pressure is very high. Here the fuel injection pressure is relatively low, but you have help from air swivel. So the mixing will be because of high fuel injection pressure as well as the air swivel. This is the highest swivel in the DI engine. So you can see this is the deep bowl in piston, also called M shape engine. The fuel, only one jet is coming in, only one spray, and that spray actually hits the piston bowl. So it will wet that particular area, and then it will start evaporating, and you can see this is the top shape. So because of this design, the air, when the piston is going up, the air will enter and the air will have very high swirl inside this bowl because of this shape. So the air will be swirling at a very fast velocity. So if you look at the direct injection engines, these are two design philosophies. One is high swivel, the other one is low swivel. So high swivel design, as I mentioned to you, can be deep omega shaped or M type engines. Low swivel or quiescent engines are characterized by shallow bowl in piston, large number of injector holes, and high injection pressures, okay. And smaller engines will have higher swivel. Larger engines will tend to become more quiescent type, okay. So the bigger engines, like for ships and for locomotives, will tend to become quiescent type combustion chamber, and smaller engines will tend to be more high swivel type, okay. Now if we look at the swivel in diesel engines, so first we have to define a ratio called Swivel Ratio, okay. What is the Swivel Ratio? So Swivel Ratio is defined as the ratio of air rotational speed about the cylinder axis. So at whatever speed air will rotate at some speed, so it will have some RPM, okay, and divided by the crankshaft rotational speed, the speed at which the engine is rotating, okay. So this typically it should be about 2.5, okay. So the adequate mixing of the fuel and air is enhanced by swirling action. DI engines are really designed with a specific swirl ratio typically of 2.5, and here you see two things are shown here. One is that this is spray formation without impingement. There are two design philosophies. One is that the spray is coming out, it doesn't hit the cylinder walls, and you can see that the spray is actually moving because of the air swivel. If there is no air swivel, this part will not be there. Then you see if this spray formation is such that the liquid spray hits the cylinder walls, so then this kind of shape of spray will take place. And in this case, if you look at the combustion will not be really going all the way to cylinder walls, because the spray is not hitting the cylinder walls. In this case, the combustion wall will reach all the way to cylinder walls. If you look here, in order to create the swirl, you can do two things. One is that you can generate swirl because of the piston design, but then the design of the intake manifold also plays a very important role in generating the swirl. So if you have a manifold where the air is coming like this, it revolves around the valve, comes in and keeps the same momentum. So it will then rotate inside. So air is being directed and swirled as it enters the combustion chamber here. So there are three types of swirl. One is the induction swirl, the other one is compression swirl, and the third one is combustion swirl. So in the first induction swirl, that means the swirl is actually generated by intake manifold or by intake system. So how it is generated? So suppose you have a manifold which is tilted. So when the air comes in, it will come in this direction and then it will follow the cylinder walls. The other thing that you can do is when the air is coming in, you don't want the air to go to this side. Half of the air goes this side, half of the air goes this side, and that will disturb the swirl. So what you do is you provide a lip on the valve. So now the air that is coming in will not go through here, it will only go through here, and therefore it will aid in swirling motion. Or you can provide a lip like this. So you can actually provide lip on the valve in order to generate swirl inside the combustion chamber. So this is called intake swirl. So this you can do by during the suction stroke, forcing the air in a rotational moment, by masking the one side of the inlet valve, and by providing lip on the one side of the inlet valve. Compression swirl. So compression swirl, in the compression swirl, air from the periphery is forced into the center of the cavity during the compression stroke. So the piston is coming down, imagine something like this. When the piston is coming down, suppose you have, this is the cylinder head, okay. So when the piston moves up, this area will reduce, this area will not reduce so much. So what will happen? The air will be squeezed and this will start moving in, okay. So basically the air will start moving in depending on the piston. So if you have this kind of piston, this kind of a swirl will take place. If you have this kind of a system, there could be two swirls. If you have this kind of a system, there may be swirl like this. So many piston designs can be made, and this compression swirl can be generated inside the engine. Combustion swirl, of course, this is created due to partial combustion. This is called combustion induced swirl, and this is normally in the pre-combustion chamber. As I showed to you, direct injection, indirect injection engines. So the combustion takes place inside the pre-chamber or swirl chamber, and then from there the combustion proceeds in the main chamber. I will explain this to you later in my lecture. So pre-combustion chamber, air fuel mixture becomes rich and forces the gases with very high velocity from the pre-chamber into the main chamber, and this creates high temperature and a particular direction of motion, and this provides very good combustion. Okay, so this is about the swirl. Now let us look at what are the processes that are happening inside these combustion chamber. So first we will look at direct injection open quiescent chamber with quadruple valve. Quadruple valve means every cylinder will have 4 valves, 2 for inlet and 2 for outlet. Okay, so basically this is, as I mentioned to you, quiescent chamber is suitable for large, slow and medium speed engines, either for very large engines which are like ship kind of engines up to 1 meter, or medium. So when you say medium, you're talking about locomotive engines or very high truck, high power truck engines. Okay, there's sufficient time for fuel to be injected into the cylinder, since these are slow engines. So slow engines means they are rotating at very slow speed. So there is, for completing one cycle, you have lot of time available to you in terms of milliseconds. Okay, you have very large number of milliseconds available for you for combustion, for mixing, for injection, for combustion, everything to take place. In case of faster engines, the same thing has to be completed in smaller time, shorter time. Okay, so there is sufficient time for fuel to be injected into the cylinder and for it to be distributed in the entire combustion chamber and to be thoroughly mixed with the air charge. How does it happen? So basically you see here, these are the two valves, okay, these are the two intake valves. So the fuel is, the air is coming in and then it undergoes some swirling and then it comes out, and from here the exhaust takes place. So in direct injection open quiescent chamber, this is without air swirl, so there is no hot gas velocity. More heat is available for doing useful work because the heat loss is low from this, and therefore higher BMEP, higher brake mean effective pressure can be obtained. That means you can operate them at very high load conditions. So mixing of the fuel and air is achieved by the intensity of the spray, by ability to distribute the spray in the entire combustion chamber, and by finally atomizing the spray. So injector directs the fuel towards the shallow walls of the combustion chamber. I told you these are very shallow walls. The injector is directing the spray in this direction. Air is quiescent, there is hardly any turbulence, and mixing entirely depends on the discharge spray distribution and atomization. So let's look at what are the things that are happening inside the combustion chamber, quiescent combustion chamber or semi-open volumetric combustion chamber. So semi-swirl induction port with an inclined centrally located injector. So you can see this is the valve and this is the injector. So the air is coming in and it is undergoing some swirling motion. Okay, so the air comes in and it starts rotating like this. Then this is the inclined injector. So injector hole, central hole is here. So from here what you are doing? You are injecting the fuel spray. Where? Here. Only in this chamber. And as I mentioned to you, this is little offset. This is not really in the center. So you can see this is little offset. This is not in the center of the bore. This is little offset. Why you do it? So that you can create higher intensity swirl. Okay. And here the fuel is injected. So fuel is going to hit these walls. It is possible. Okay. There is very high swirl. And when you are injecting at the end of the compression stroke. So piston is already very close to the top dead center. There is hardly any volume here between the cylinder head and the piston. Then you see this spray that you have injected, some of the droplets will atomize, mix, and then the combustion will start. So the combustion will start and there is swirling motion. So slowly what will happen is that combustion will take place inside this chamber. Okay, here. And then pressure will start increasing and this pressure will start pushing the piston down. So once it pushes the piston down, there will be more volume available here. So once the volume is available, the combustion will then proceed from this bowl into the main chamber. Actually this bowl is also a part of the main chamber, but here it will come in and utilize this air. Okay. So this is what happens in quiescent and semi-open volumetric combustion chamber. Okay. So in semi-open there is some swirl, quiescent there will be no swirl. Direct injection volumetric combustion chamber. So as I mentioned to you, in direct injection, the fuel injection takes place. Because of the swirl, this motion takes place, and then you see this starts burning here, combustion starts, and you can see the swirling happening, and then finally this comes out. Okay, so this will then start, the flame fronts will start moving in the main space, that is this space. Okay, now what we need to do is, see, in an engine, when you want to study the combustion, what do? The first thing that you do is that you are interested in looking at the pressure crank angle history of the engine, and that gives you a fairly good idea of what is happening inside the combustion chamber. So what you do is that in the cylinder head you put a piezoelectric pressure transducer, and in the crankshaft you put a high precision optical encoder. So when the shaft rotates, for every 0.1 crank angle degree, it gives one signal, and then it triggers the piezoelectric pressure transducer and captures the pressure signal. So then you can calculate theta, crank angle degree, and cylinder pressure. Okay. So basically in the engine, as you have studied already the first level course, in the engine most of the exciting part of the combustion cycle is from say 40-50 degree before the top dead center in the compression stroke, and maybe 60-70 degree in the expansion stroke. So that is one area which is most exciting. So this is the motoring diagram. Motoring diagram means just you are compressing the air and expanding, no combustion taking place. Okay, so this is the motoring diagram, and this is the firing diagram. Firing diagram means you put the fuel. Now let us see when things are happening. So suppose at this point the injection is starting. So this is the bowl. Here you have these swirling motions. Okay, the fuel is injected. So the injection starts here. So once the injection starts, nothing will happen. The pressure will not change because there is no heat release. Once the combustion starts, ignition happens, combustion starts, then what will happen? You will start seeing some pressure rise. So this firing diagram will start separating from motoring diagram, and then the combustion proceeds. Okay, combustion reverse flow into the cylinders. Reverse flow into the cylinder means it will start going into the main chamber. So this is the peak of the pressure. Okay, and then you will stop the injection. Injection is still happening, so you will stop the injection. So this will be here, and then slowly all the fuel droplet that you have injected will start getting consumed. All of it is burned, all of the heat is released. So that will happen here. Okay, so this is the products of completed combustion. Formation takes place, and then slowly this will start coming down, and at some point this will merge with the motoring diagram, almost merge with the motoring diagram. Okay, so this is the area that is most exciting for us. This is the area which is going to give you power output from an engine. Okay, now let us look at the third design, which is the small direct injection semi-open combustion chamber with helical induction port. So here you can see the induction port is such that it gives you large amount of swirl. So the extra air movement is achieved by utilizing helical or partial vortex form of the induction port. So the induction port is such that it gives already some movement, helical movement to the air. The incoming airflow is given helical twist or semi-vortex motion about the valve stem. As a result, a high degree of air swirl is generated within the curved port passage. Now, the next type of combustion chamber is direct injection film type or M type or MEN type, many synonyms of combustion chamber which are illustrated in these phases. So this is, now we are talking about this type of combustion chamber where you have very high degree of swirl in the chamber and single hole nozzle injecting the fuel at not so high pressure. So here you see this is the motoring diagram, and here you have start of injection. So the fuel is injected in a single jet, and there is very high degree of turbulence inside this chamber, and then you see this area will get wet. This area of the piston will get wet. Now this area of the piston will be hot because of the heat that it has absorbed from the previous cycles, right? So it will help the fuel evaporate. So the fuel will start evaporating after absorbing the heat from the hot piston surface and start evaporating, and then it will be mixed with the air because of high swirl motion. So that's what happens. So ignition starts. So once the ignition starts, the firing curve will start separating from the motoring curve, and then the entire combustion chamber will be filled with fire, and then it will start coming into the main cylinder. So this is that position, and then here you are doing the end of the injection. So this is that position, and then finally everything will be filled with hot combustion products. All the droplets are burned. That is here about 20-25 degree after top dead center, and then so you see here one of the important things that I would like to mention here is that one engine cycle is 720 degree crank angle, but out of that the most exciting thing happens in only like 40-50 degree 60 degree crank angle.